The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, so yeah, problem set 2. There's a lot of work done. Congratulations to all the workers. 16 trillion hashes performed. How can we prove that? So this is sort of a personal sort of gripe that I hear a lot, that people say that proof of work doesn't scale. And that really bugs me because sometimes I think I sort of know what they're talking about. And they mean like, Bitcoin doesn't scale, or like these blockchains have poor scalability properties, which sure, they definitely do. But proof of work, it scales sort of perfectly in a theoretical sense. Like there's nothing that can scale better. You can prove an arbitrary amount of work in O of 1, right? So in this case, well, how big were these headers? They were like less than 100 bytes, right? 100 characters. And with that space, you can prove actually the entire work that happened over the entire problem set. So yeah, blockchains, whole bunch of scalability problems. There's complex systems, all sorts of scaling issues. But proof of work itself in this pure form scales really great. Okay, so question. Not super intuitive, but how do you prove all the work ever done throughout the entire problem set in one line? Does anyone have any intuition about the sort of, how do you prove all the work from all 1,800 blocks with just one piece of data? Yeah.
Well, you know that for each block, 2 to the 33 work had to go into it, so you just need to know the number of blocks produced times the...
Okay, yeah, so the thing is, how do I prove the number of blocks without showing all of them? Right, so it's kind of a weird trick question. Andrew Miller, I remember Andrew Miller, who's now a professor at somewhere, Cornell, who was not during the time, sort of wrote about this initially in the Bitcoin forums. What you do is you just show the luckiest block, and I've not yet defined luckiest block, but in this case, it was mined by Turtle. This is the block. The previous block reference was 0065A2, Turtle 1654244, and the hash of that block is 000C49A414, blah blah blah. So anything interesting or novel about this particular block that you can see? It's not. What? It's better. It's like there's more work. So we didn't count the things as having more or less work just based on number of zeros. We just looked at the threshold. Did it have enough 0 bits and accepted or rejected? But in this case, these 4 bytes, right? You needed 4 bytes and then 1 extra bit, right? You needed 33 bits. So these 4 always were 0. But then you see in red, there's another extra byte that's all zeros, and another extra half a byte that's all zeros. And then a C means for that, nibble, that the highest bit was 1, right? So you've got this red stuff. There's a byte and a half extra, or almost a byte and a half extra. So yeah, so what you can do for a compact proof of work. So if you look at this again, there's, 4 green bytes, byte and a half that's red, right? So that's 5.5 bytes, so 44 bits. And 2 to the 44 is 17 trillion, right? If you do it out, 17 something, which is what we expect, right? That's sort of our proof, right? We did 16 trillion hashes for our calculation, and it shows up here. And another way to look at it is we needed 33 bits for a valid block. We have 44 bits here. That's 11 bits extra. That's 11 bits of like being lucky. And so that's 11 bits. 2 to the 11 is 2048, which is pretty close to the 1862 that we actually performed, right? So in this case, we're a little lucky. We might have only had 2 to the 10, and then we could only prove that we'd done like 8 trillion work instead of 16 trillion work. So there's probabilities here, but this is an interesting property that it actually does work. You can prove all the work, to some approximation, usually within a factor of 2, that the system's ever done just with one block header. So yeah, this is fun because another way to look at it is that you've got this sort of meta game where for every block found, take the, I'm doing a hash and I need to find a hash with a lot of zeros to prove that I've done work. And you sort of like go a level deeper and say, okay, I'm finding a block and I want to prove that I found an even better block than everyone else, right? The entry for admission here is find a valid block. And then from those blocks, since it's a uniform distribution with ones and zeros, you're going to have this tail end of like happen to have lots of zeros that you didn't need in the beginning. And that can prove all the work ever done. There's a really interesting paper called Hyperloglog that uses this for non-Bitcoin applications, that uses it for like set counting, where sort of like on a website, you want to see how many unique visitors you've gotten or something. And you can store that in O of 1 space. Because you could keep track of like, okay, let me keep track of every IP address that's ever visited or something like that, or cookie. But instead you sort of hash them, see if the hash starts with a bunch of zeros or any arbitrary character, and then just store the lowest. And then every time someone visits, hash it, compare. If it's lower, replace. If not, ignore. And then you have a very compact sort of indication of how many visitors have visited. Anyway, that's like a super high-level view of it. But if you're interested in this kind of stuff, Hyperloglog is a paper. It builds off of some other things. It has nothing to do with Bitcoin other than this property, where you've got this like random function and you see how many zeros are in it. But I don't know. I think these are kind of cool. And so to me, this is like a fun, this is not used in Bitcoin, right? In Bitcoin, you actually download all the headers. But people have sort of written papers about how you could use it. If long-term the headers are, big, you could, have some like checkpoint where like, look, I proved all the previous work and now I build from there. So, any questions about this idea? Yes?
It's not really a proof, it's just a probability weighted,
Yes, but the proof of work itself is the same, not a real proof, right? Because you might have gotten lucky. So finding a block, it is the same. It's sort of like, well, that's not a proof. There could be luck involved. There could be probability. But it's the exact same luck and probability that the underlying proof of work uses. So there's no like further reduction in security or certainty because of this. Not really. And so I remember talking about this with someone a few years ago and saying, yeah, proof of work is sort of a misnomer. It's not really a proof, right? Maybe it's an argument of work or some kind of probabilistic argument of work. How could you make it more certain as a proof? There's a bunch of ways. One way would be to have multiple nonces, right? Where instead of just finding one nonce that satisfies it, you have to find several replaceable nonces and then like iterate through them. That would be a much more certain proof. It would remove the idea of probability to some extent. It would also completely break the system in a way that's like fairly unintuitive. And so I always was sort of joking, like I should make an altcoin where you've got like multiple nonces and you could be like, yeah, it's for more security. And then people would, buy it, but it completely breaks. The completely broken incentives and system, maybe I'll hint at, I'll let you guys like think about it till Wednesday and then, draw it out and be like, why wouldn't this work? It's kind of fun. It breaks in subtle but bad ways. This is sort of talking about like proof of work optimization. So if you look at this slide anyway, you've got these headers, right? Or blocks or whatever we're mining. So you've got KZK17, Tom Riddle, Thalita, like all these people mining. It's interesting to see what people use. Some people use like what looks like base 64. Some people just used like a decimal number, all sorts of different things. Who knows? There was also a lot of invalid blocks with valid work submitted, where there was like 4 or 5 different things submitted MySpaces. So those didn't count. But actually a lot more work was done, and that's not even counting the human work of doing all the assignments. So sending this over the wire or storing it on disk, some inefficiencies may jump out at you. What do you think you could do to make this more efficient or compress it or? Yeah.
All of them start with zeros.
Okay, that's an easy one. Oh, this doesn't work when I gave you the slides because you can just look at the next slide and yeah, oh, oops. Okay, never mind. Yeah, so the first 8 characters are always going to be zeros, right? Like by definition. If it's not, it's an invalid block, so don't even bother sending it. So if the first characters are 0, don't send them over the wire. Just have that implied, right? I just start at the whatever 9th character. That saves. Well, really, you'd have this serialized in binary, so it only saves 4 bytes. In this case, in our case, it would save 8 bytes. That's cool. And then also the entire previous hash, when you're sending a list of 5 here, like here, in order for it to be valid, this has to be the hash of the line above it. So just don't send the whole thing, right? Just send name nonce. The hash is also computable from anyone receiving it. That takes almost all of the space, right? And we could sort of compress this entire blockchain to just the first line, and that's the only full line we need. After that, it's just name nonce, and we get rid of like what 70-something% of the space. That's pretty cool, right? Yeah, this kind of header optimization is also very much possible in Bitcoin, and it's not implemented. It's not done. If you want to, you could program it, change Bitcoin, have this, like, make a pull request. I mean, we've discussed it, and people are like, yeah, that'd be cool, but no one's done it. So if you want to like leave your mark and be like, I'm a Bitcoin Core contributor, and I optimized the proof of work propagation system or something, sounds cool, you could do this. It's not too hard. You got to learn how Bitcoin works and all the different messages and stuff. So it's a little annoying. I think the main reason people haven't done it is because it's this is not the slow part, right? This is not the critical path, not a bottleneck in the actual system. Generally, the proof of work verification is pretty quick. The headers are a total of like 40-something megabytes now, 50 megabytes maybe. So you could definitely reduce that by a significant extent, but no one's bothered because there's so many other scaling issues that are more pressing. But it's kind of cool, I think. Someone might. So yeah, that'd be a fun thing to do. If you did that, right, would that be a soft or hard fork? If you said, okay, I'm going to now send header messages that are truncated, right? I'm going to leave off the 4 bytes that are always zeros. Bitcoin is also, the difficulty requirement here is basically the same as in Bitcoin. I'm going to, have the implied previous block hash, things like that. Would that be a fork? Actually, it wouldn't, right? It's sort of a non-fork. There are lots of changes you can make. So I know Neha talked about, soft forks and hard forks, changes you can make in the system that affect consensus. But there's a lot of changes you can make that optimize it that don't really affect other people. So in this case, it would just sort of be a wire protocol change, and you could easily maintain backwards compatibility, right? So in this case, you say the header optimization, it's not a fork, right? What you do is you'd have a new message type, like truncated header or something. And then when you connect to nodes, you say, hey, do you know about this new message type I'm using? And if they don't know what you're talking about, or usually they say what version they are when they connect, and you're like, oh, you're an old version, you don't know about this. I'll just keep saying the old header type. And even if I store the new truncated headers on disk, I can recreate the old one pretty quickly, right? By tacking, performing the hash, tacking that on, sending it to you. So I can be compatible, backwards compatible and forwards compatible, no softworks needed. The old nodes, they don't even see that this happens. They might see that there's a new version or a new message I'm not aware of. They ignore it, everything seems fine. So these are kind of the easiest, they're not forced, the easiest changes in the system to get through because there's no real coordination needed and it's backwards and forwards compatible. So that's cool. So some example non-forks. A lot of them are internal only that you can't even see from outside. So for example, compressing blocks or compressing your database. That's fairly straightforward, right? It doesn't seem like intuitively, it seems like, well, these are all like random numbers and hashes. You can't really compress those, right? Because they're random. In practice, you actually can. People reuse public keys a lot. And so you just see the same pub key over and over. So you do some pretty simple encoding and you can make those smaller. Also, the amounts is 8 bytes. So if you're sending someone, 1 Bitcoin, that's, 100 million. And people like to use round numbers. And so those get compressed pretty well. And generally, there's, much smaller. So the top bytes are usually zeros. So you can compress it a decent amount. But no one has to know that you're compressing, right? That's all transparent. When someone connects to you, they have no idea if you're compressing or not on disk. Something like faster signature verification, where there's been enormous amounts of work in optimizing the code for that, making assembly, stuff like that. Nobody knows you're doing it, right? They're just like, oh, he's asking for blocks quicker than this other person. Maybe his network's faster, maybe his CPU's faster. So these kinds of are changes that are purely internal, nobody needs to know. That's kind of cool. Other non-forks are peer-to-peer non-forks. So the truncated headers maybe, where you can say, hey, I'm going to send you less data over the network. You identify at connect time, and you default to the old behavior. People don't know what you're talking about. So there's one called compact blocks. I didn't describe it, but you can probably guess what the idea of compact blocks is. Anyone want to venture a guess what those do? Block. So it's not the header that's compact, but the whole block. How would you compact a block? Yeah.
Get rid of all the fields that aren't necessary, like version and.
Yeah, actually, that would work. That's not what they do. There's a really big like 2x redundancy. So the basic idea is transactions are propagated and then a block's propagated. Where's the redundancy there? Yeah, the transactions, the block, you've probably already seen them, right? You see the transactions and then the block comes out. Most of it in general, 90-something%. It's like, yeah, I already see all those. So compact blocks is a way to say, hey, here was the block. Here are all the transactions in it, but I don't show the whole transaction. I just show like the TXID, the hashes. And then you can say, okay, 90% of those I've already seen, so we're good. Here's these 50 transactions I have not seen, please give them to me. So it's interactive, right? It's like, here's the blocks with just the transaction identifiers. Okay, what do you need? Okay, I need these 10. Okay, here's the 10. And now I can reconstruct the whole block. So the block goes from being like a megabyte over the wire to something like 10 kilobytes. But it is a little slower in that it's like a multi-round thing, right? It's like, here's the compact block. Okay, I need these extra things. Okay, here's the extra things. So a little bit more complexity. If you're really optimizing for latency, then you don't want to use this. But in general, it's a pretty big gain in terms of bandwidth, which can be taxing on full nodes. I run there's a full node on the first floor in the little rack, and it uploads 3 terabytes a month or so. Depends on how much people are using Bitcoin. Like in December, everyone starts downloading it and installing it, and there's a lot of bandwidth needed to like sync people up. Another non-fork was the Bloom filters, which full nodes can then say, hey, I will perform Bloom filter calculations for you. And light nodes can connect in, like I said 2 weeks ago with SPV. Light nodes can submit a Bloom filter, say, hey, when I download a block from you, first filter the block. Match all the transactions against this Bloom filter and only send me things that match. That's not a fork, but it's a fairly involved change in the peer-to-peer code. Okay, any questions about these peer-to-peer non-forks? Good, cool. There's another aspect called standardness, where you haven't soft forked something out. You haven't declared something invalid, but you can declare it non-standard. And what that means is when your node sees a transaction, right, coming over unconfirmed, a transaction being propagated through the network, and it's got this property, you say, oh, that's non-standard. I'm going to drop it. I'm going to ignore it. I won't propagate it onto my peers. I won't ban, it depends. I don't know. Do I ban the person submitting it to me? I think you don't. But I ignore it. I don't propagate it. So it doesn't really get around the network. When most of the peers on the network have these rules of non-standardness, it's going to be very difficult to get your transaction out there. However, if you see this non-standard transaction in a block, you accept the block. You say, okay, well, that was this weird thing that I didn't like, but since it's in a block and someone did a lot of work on it, I will accept it. And it's a little weird, right? Like, why have this? It's sort of something that's not quite a soft fork, right? It's showing that we're discouraging this. We think it's non-standard. The miner's software by default will also consider this non-standard and not mine it. But if someone else is mining it, we're okay with it. And so what you can do is you can stage future soft forks this way. Right? So for example, in Segway, oh, I didn't talk about Segway at all. I'm gonna have to do that next week maybe. Okay, so in Segway, Segway was like the biggest soft fork ever in Bitcoin, and it occurred last year. It changed the output scripts to say just like, it changed the output scripts. So before you said, op dupe, op hash 160, the hash, op checks, op equal, whatever. Here it just says 0, just pushes a 0 byte, and then pub key hash. And that's it. And if you actually interpret that in the stack, no signature is needed, right? You push a 0 to the bottom of the stack, you push a pub key hash on top of that, and then your execution halts, and you're like, well, there's a non-zero piece of data on the top. I interpret non-zero data as true, right? Same way C does. So it's true. You don't need a signature at all. So that's sort of the weird Segway Softwork where they said, no, what used to be considered true without a signature, we now sort of template, and we say this means check pub key hash, right? This means the same as opdupe, op hash 160, hash, op equals, op check sig, op check sig, right? So what you actually do is, you need to provide the pub key that this hash is into and then check a signature. It also defined 1, 2, 3, up to 16, and left this undefined and said, look, these are now non-standard. Before, I think they were already non-standard, but the idea is if you just push a 1 on the stack and then push some data, well, I guess no signature is needed. But now they're non-standard because it means we're going to use these next. The next softwork will define what some piece of data means. Maybe it's a new signature scheme, maybe it's a new kind of program where you put some data here. But it's non-standard, so if you try to make a transaction that's using like 2 and then a data push, all the nodes will be like, yeah, I'm not ready for that. Like I haven't seen that. And if you see, I think in your error logs, if you see a block with a bunch of these kinds of things, it'll give you a warning. It's like, warning, people are using stuff that your software doesn't know about. You might need to upgrade. So there's a bunch of warnings like that where like, warning, like the last, some percentage of the last few blocks had these things. So people are doing stuff that you're not considering invalid, right? You're not gonna like refuse the block, but you're also like, this is something I don't understand, right? And I've specifically coded it in as non-standard. Okay, so any questions about non-standardness? Neha talked about soft forks and hard forks, right? And I will go through a bit more detail about sort of how these end up working and how these interact with miners and nodes. Did people have questions about soft forks and hard forks before we start? Like, sort of got the general idea, right? Soft forks add new rules, hard forks remove rules in general. And this is miners, okay? So the miners have sort of a unique role here. It's not just the same as a full node. A miner, decides what to put into a block that they're mining. And so they do have a bit more influence in these fork decisions. Okay, so a soft fork would be, for example, saying, okay, all output amounts must be odd, right? You can't send an even number of coins to anyone anymore. That would be a weird, silly fork. Wouldn't really impact the usability of the system, but it'd be kind of dumb, but you could do it. And you could say, okay, well, if I see a block, if I see a transaction which outputs, if any of the outputs have an even number of Satoshis, invalid. You got to do odd. Potentially leading to the loss of 1 Satoshi per transaction. Well, the fees. 1 Satoshi per block may end up being lost due to this. So, so here I'm saying an A for adopter and I for ignorer. Now, people may ignore the fork because they disagree with it. They don't want to do this fork. Or they may do it because, they may just not even know that this software exists. It's a, giant decentralized system, and it's hard to know how to communicate with everyone, right? So there is like, bitcoin.org. There's also bitcoin.com, where the guy doesn't like the Bitcoin developers and says they're bad. Anyone can just register these things. There's a Bitcoin Twitter account that was purchased recently by someone who wanted to argue about these things. So like, there's no one really in charge of this. And then there's also like different implementations. There's the real Bitcoin, which is run by this bunch of crazy people who say they control Bitcoin and that everyone has to pay them taxes in Bitcoins. And they're, yeah. But they're all running Bitcoin, right? They all are in consensus and doing these transactions. So ignoring could be any number of things. If you have a soft fork where you're saying, okay, we're now adding this rule, but none of the miners are enforcing it. None of the miners even know about it, potentially. Here, it just stops, right? You say, no, I require that all output amounts are odd. And then every block has these even amounts. And you're just like, okay, no, that's not a valid block, that's not a valid block. You will never see a valid block again, right? None of the miners are enforcing this rule. but you are. Everyone's ignoring it, and they say, everyone's ignoring it, everything seems fine. You just self-impose this new rule, making you incompatible with the rest of the network, and from your perspective, everything stops. And no more blocks occur, and the system's over. Or potentially, if your soft fork is some like weird rule that nobody knows about and nobody breaks anyway, we can say, okay, the sum of the outputs of all, the sum of the outputs in a transaction must not be a Carmichael number. Okay, you could have that rule. Probably no one's wait, there's a lot of small, something like that, right? Where no one's breaking it anyway. Then from your perspective, everything's cool because everyone's already obeying your rule because even though they don't know about it. It's kind of silly. Another possibility is, let's say a minority, somewhere 1 to 50% of the miners adopt this rule and say, yeah, we're going to enforce this new rule, right? All output amounts need to be odd. So the idea is you say, yes, only odd numbers. And the majority actually of people don't care about odd or even. So the majority, they still go off on their own chain, but you split off into your own faction and you say like, nope, we're the odd bunch. And both of those chains are viable. Blocks come out here, maybe quite slowly if it's only a few percent. Blocks still come out here. So you've got these, odd thing, odd, and then you've got regular. And the regular is going to be longer, right? The regular is going to be potentially a lot longer. But from the people here, they're like, we don't care if it's longer, it's wrong. They use even numbers. That's just plain old wrong. And these people are like, yeah, we can sometimes see it, but actually we lose track of it very quickly. After here, we start seeing block advertisements like this, and we're like, what? We're over here now. We're way past that. Why are you talking about this stuff from like weeks ago? So they just disconnect. It's pretty ugly, but that can happen. Now, if you have the majority of the hash power, this ends up being longer. The odd blocks end up being longer. And everyone gets dragged along, right? No split. And now we have a new rule, right? Even though they didn't know about the rule, potentially. So they're like, what the heck? Half my transactions don't work. Some of them do, some of them don't. I don't know what's going on. I just randomly adjust my fees until it seems to work. And then my transactions go through. They should probably find out from someone, oh yeah, there's a new rule, only odd numbers. And then they, that rule is imposed on them from the miners, essentially, and the rest of the network. And essentially the same thing here. When you get to 100%, there's none of these orphans, but these orphans would actually be like this, right? Because everyone agrees that this is valid, and then some of the people aren't aware of the rule and keep mining off of these, what they consider valid blocks. So it's a little bit different topology. Okay, so that makes sense, right? Any questions about soft fork mining power rules? One other aspect is if you split here and then later on you get a majority and you pull ahead, you will reorg out the ignoring side, right? So we split off with 10% of the hash power. We've got our much shorter chain where we only have odd numbers. At some point we convince the rest of the miners that no, this is the way to go, that even numbers are really screwing up this system. And we get the majority of the hash power. And then we overtake the even and odd mixed chain. The people who have not updated their software and are ignoring the fork, they will reorg out. Because from their perspective, okay, I was on the longer chain. Now there's this other longer chain. They both look valid. And when I see two valid chains, my way to decide is who has the most work. And so this one pulled ahead in terms of work, so I switched. So it's a weird, this has never really happened that I'm aware of. They were threatening to do it last summer. They had hats that said UASF, I don't know. So yeah, there was all sorts of stuff on the internet and Reddit and Twitter about doing this with a minority of hash power. They didn't though, or they did. And they say they did, but everyone else says they didn't. I don't know. A lot of arguing. Okay, so that's another weird aspect of it. Okay, hard forks. No miner support. What happens to those adopting it? Nothing, right? Everything keeps working. If you say, okay, we're now going to allow every transaction output, every transaction can have one extra Satoshi gets created. It's just one. It's no big deal. And it's quite limited. But we want to, compensate people for using Bitcoin. So when you have you have your inputs, you have your outputs, you can add one Satoshi, and you get a free Satoshi per transaction. The previous software absolutely does not allow that, right? If you're just generating money out of nowhere in these transactions, it's not okay. But these guys will say, they'll see that the transactions they do that with are not confirming. But otherwise, they're okay if you don't add a Satoshi. And so the system works, nothing happens, they just see everything. With a minority of the hash power, something like 10, 20%, you get all these orphans. You get all these dead ends where you see a block, okay, and it's got this, at 1 Satoshi per transaction bonus, great, but it keeps getting orphaned out because you still consider, right, so you see, okay, here's this longest chain without the bonus, and then you say, oh, here's a block with the bonus, cool, maybe someone builds 2, great, but this keeps getting longer. And you keep trying, but you keep getting overpowered, right? Because you see both of them as valid. You're not requiring that there's this 1 Satoshi bonus per transaction. You're just allowing it. And so you see, oh, this is cool. Oh, no, got reorged out. So you see all these little starts that get reorged out, and you basically stay with the same chain. You don't split. These people also see a bunch of invalid blocks, right? You'll see it on the network. Hey, someone keeps sending these invalid blocks much more frequently than usually. I don't know why they're doing that, but they've got invalid transactions. I ignore them. Here, majority of hash power, you split, right? So once it's the majority, and these are the, the bonus, the plus ones, they pull out ahead. These guys don't actually care that they have a majority. After the first block, they don't see the rest because they ban. So if someone submits to you an invalid block, you ban them. You ban their IP address for like 24 hours or something. You're like, I don't know what you're doing. You're crazy. Disconnect. So you won't really see this pretty quickly. These guys don't have the bonus. They're still on their same old blockchain. It may be much slower, right? Because a lot of the hash power is now moved to this other chain. And these guys say, oh, it worked. Cool. We've got our new, bonus coin chain. And now we're, stimulating the economy, everything like that. Job creation. Okay, so, and then these guys, slows down. And then if you have 100%, well, stops. For the non-adopters, no more blocks come out. This is the end. Everyone's gone to the, job creation chain. And look, there's not really a split anymore. It's just, the new rule. Okay, so any questions there? This sort of grid so far. Then another way you can do it is combine these. To say, okay, we're going to do a soft fork and a hard fork at the same time. And actually, many times that people say hard fork, they actually mean this. So the nomenclature is pretty ambiguous. I like keeping these terms very distinct and pure. So like a soft fork is purely increasing the number of rules where, must be odd. And a hard fork is just reducing rules. So yes, we will allow but not require a transaction to have this property. And then to combine them would be something like saying, we allow this new thing that was not allowed before, and we require it to be true. So for example, every transaction must introduce 1 new Satoshi bonus. That would be both a hard and a soft fork, right? Because now this, if you're doing this, you no longer consider the old rules appropriate, and there's a complete mutual disagreement on the rules. Some people have called this full fork. Who called it that? I forget. Greg called it a bilateral hard fork. We don't have good terms for these things. A lot of people refer to forks that have both as hard forks. So it's somewhat ambiguous. I think it helps to keep these different terms. But it's a different setup. It's sort of the union of these two things in some way, in that we enforce, we allow this new thing that was prohibited before, and not only that, but we require it. So if 0% enforce the new hard fork, well, the adopters, it just stops, right? They're requiring this new thing, it's not showing up, it ends. These guys, nothing happens, right? When there's a minority, it will split off. It'll split off with the new rule set, and the new, bonus coins or whatever, and the ignorers, they see that it's, slower because some people have left, some mining power is left. When you have a majority, you also split off, and ignorers, again, it's slow. They're not going to adopt because they see the new fork is invalid. In this case as well, they will, these guys won't adopt here because they see it as valid. And then for the full thing, for the 100%, the adopters, new rule, and these guys, system halts. Okay, so any questions about full fork or bilateral fork, or whatever you want to call it? Yeah. Hey, it works. Okay. Okay, cool. Okay, where am I? Yes, bilateral, hard, full. We don't know the good names for these. But yeah, it's essentially a soft fork and a hard fork coupled together. And it's actually this is much simpler or easier to produce. And then if you just start changing the code, you're probably going to create one of these, right? You have to be very careful. If I want just a hard fork, right? I'm very careful that everything that used to be valid is still valid, and I'm just rescinding one rule or one set of rules. If you just, it's very easy to inadvertently create this when you're trying to make consensus changes. Yeah, there have been, did Neha talk about the 2013 fork? I don't think so. Okay, so little anecdote. I remember I was in the airport. I got to Nagoya airport and opened my laptop, and Bitcoin went down to like $20 from $30. And it was like all over the internet, like, oh no. And there was a inadvertent hard fork due to the Berkeley DB to Level DB transition in the software. No, it was old, the 0.7 was using it used to be everything was using Berkeley DB for the UTXO set in the blocks. And then they switched to Level DB, and then it was okay for a month or two, and then someone mined a block that was had a bunch of inputs or something. I don't remember exactly the reasons. And the new software was yeah, that's cool. And the old software said it wasn't okay. The thing is, it wasn't clear why, right? There was no defined this should be invalid. It's this looks valid, but the database, the Berkeley DB layer gave an error. And so it's well, the database says it's bad, so it's not a good block. So that was sort of a weird, unintentional consensus change. What happened was, so it seemed like it was a hard fork. The thing is, it was a compiler time option dependent hard fork. You compiled it with a different Berkeley DB cache setting, then it would work. So it was not, sort of ambiguous. And people rolled back though. They were on IRC and they're talking to the different miners. They're what's going on? There's 2 different forks being built. And they told the people who were, to some extent in the right? The new version, which seemed more correct, to stop mining. And they did. And then the old version with the Berkeley DB caught up. And then they sort of restricted their block size. It was something to do with having too many file locks open or something like that. So that was it was essentially a hard fork. They sort of stopped it and then went back, so there wasn't a hard fork. But then months later, they're okay, we're going to all transition to Level DB because we're not even sure what the rules are. Yeah.
Yeah, you're right. It was Berkeley DB had a hard limit on the number of blocks per update, and they produced a block with way too many. So Level DB was okay, and Berkeley DB was this isn't valid.
Yeah, and the thing is, they definitely did at the time, people were sort of running around screaming why, after the fact, they're that's why. But at the time, people were sort of talking really quick and what's going on? Bitcoin has failed. Sell all your Bitcoins. This system doesn't work. Because no one really knew what was going on or why some versions weren't working. So yeah, that was sort of an unintended fork. It was a little scary. And then the price went back up after that because it was hey, we can work through this, guys. So that was a hard fork, right? The old software would not allow these blocks that opened a bunch of file locks, and the new software did. And so that was probably the one real hard fork that Bitcoin has been through. There were a few maybe in 2009 that are fairly ambiguous because there was no actual split. I think there's also a hard fork that's happened but it didn't, it's a little weird. It has to do with the timestamp in the block header and how it like expires in 2106 once you run out of bits from Unix time. Like 1970 plus 2 to the 32 seconds is like 2106 in January or something, I don't know. And so they actually did a hard fork. But the thing is, the hard fork wouldn't diverge until 100 years from now. So it's sort of like, whatever, everyone will have updated by then. If someone's still running software from 2015 in 2106, they will diverge, but that seems unlikely. So there's a lot of weird stuff like that. Okay, fun variant. Some people call it firm fork. People call it evil fork. I think Peter Todd called it evil or firm. I don't know. This is a fun one. It has not been attempted, and it's. I remember talking to people, and they're like, "Don't talk about this. The miners don't know they can do this, so just." And I'm like, "Come on! Like, they don't know they can do this. It's kind of like." Okay, so how would you do this? Make a soft fork. It's a hard fork, right? It completely changes the rules. However, it looks like a soft fork to non-adopting nodes. It's kind of crazy. Well, the proof of work for the new chain is a empty but valid block on the old chain. So instead of your proof of work being, hey, have a header that hashes to this, say, have a header that hashes this, also a block that is valid but completely empty. We'll sort of take that as our header, right? Our header now gets bigger. Instead of 80 bytes, it's going to be 200 something bytes, but that's doable. Now our header chain is a chain of empty blocks. And our actual blocks point to that, right? We can put our Merkle root in the output address or something. We can put our Merkle root somewhere in this empty block transaction, the one transaction in the block. The old nodes will see it and say, yeah, that's a block. Someone's mining, here's where the money went, but there's no transactions in it. My transactions never confirm. You don't actually have to connect to the old network to do this, right? It's totally deterministic. You just say, okay, my new proof of work is a valid but empty block on the old one. And I commit somewhere in this to my new block. That's kind of evil because what happens is, here's the chart for this. It's basically a firm fork plus this little evil thing. The adopting, if you have no hash power, well, system halts and nothing changes here. If you have 1 to 50%, the adopting split off with the new rule. So in this case, it's sort of like a hard fork. However, the main difference from a hard fork, if you have majority hash power, the system essentially halts. It doesn't halt in that the blocks keep coming out, right? You'll still see, your software won't give you any warnings. It'll just be like, yep, block height keeps progressing as normal, as expected. We keep selling all these blocks. However, no transactions occur. And you can never receive or send money. But according to your software, everything's working fine. So this is the sort of firm, evil, sneaky, whatever part, where if you're able to get 51% of the mining and you implement this new fork, you're basically forcing everyone to update. Because if you don't update your software, if you're ignoring this fork, you can't do anything. You gotta adopt a new rule. This is scary. And I can see why some people were like, don't tell miners they can do this. Also, I remember last year, with the Segway 2x stuff, I think, they were arguing about this, and it really seemed that they were not aware of this possibility, which was sort of like, they don't know about this. Cool, I guess that helps keep things safer, because they were arguing about how they were going to rent like hundreds of millions of dollars of hash power to mine empty blocks on the old chain. It's like, you can do that for free if you just change your software to make your new proof of work an empty block on the old proof of work. But I don't think they were aware of that, so we're like, okay, let them go with that. Anyway, and so the thing is, you can see how it would really quickly turn into that, right? If you've got 75%, well, why would anyone try to mine on this? You could keep making blocks that did contain transactions, but they would get orphaned out, and everyone would you might occasionally see, hey, a block came out with transactions in it, it just got reorged out. And nothing would ever confirm. So you could see how the miners could never really get paid on the minority fork and the minority chain. So they're all going to start switching to the new thing if they want to get paid. So that's a little ugly. This has not happened. Yeah, hopefully this doesn't happen. But on the other hand, despite it being called evil, I know like Luke Jr., who's kind of crazy, but he's cool. He was saying this is how we should do a hard fork, right? We should also give people the option to, say, look, there's going to be a fork. We give you the option to adopt a different system or doing this so that no one's inadvertently left behind. So we sort of say, hey, a year from now, this is going to happen. You can either say, we actively refuse this new rule, and we've got our own chain now. We make a soft fork before that point. Or we adopt this new rule, update our software, and now we've got this new proof of work. The thing is, the new proof of work, you don't need new chips, right? You just need to do a little bit different software. Okay, any questions about evil forks? Kind of fun, yeah.
So an empty block is a block without a transaction.
Well, okay, every block has to have one transaction. So you'd have the Coinbase transaction. But any user-created transactions would not be in there. And yeah, in the case where there's only one transaction, the Merkle root just becomes the TXID of that single transaction. And you can put arbitrary data in that single transaction. The input field, yeah, we said the input field for that Coinbase transaction that generates new coins can be any arbitrary data you want. So you could put like a Merkle root from your real block in there and then write your new software to say, okay, the new proof of work is, the header with the nonce. Also, it's got to have a Coinbase transaction and then the real Merkle root in the Coinbase transaction and then build out your tree from there. So it's a little ugly, it's a little more complex. It would totally work though. And all the old software would just be like, no transactions, and all the new software knows that that's not a real Coinbase transaction. It's just a part of the part of the extended header. Okay, cool. Don't try. Well, try this at home if you want. I don't know. Yeah, seems coercive. That's evil. People call it. I don't know. Okay. Yeah, fork coordination. How do you sort of go a level up from this? How do we know to do all these things? Reddit, IRC, Twitter. There's sort of, these systems exist on the real world and people talk. Like the meeting I was at last week. We actually didn't talk about forks much. We sort of did. But, the developers get together, companies using Bitcoin, all sorts of stuff. On Wednesday, people were arguing about Mast versus Schnorr and which is more important, which we should try to soft fork in first. Not much gets done. So it used to be called BIP9. That's still there. Bitcoin Improvement Protocol 9. It was the idea in the header field, in the version field, you can sort of set these flag bits for which soft forks you're adopting, right? So that you indicate before adopting a fork which one you're ready to adopt. And then you don't actually implement the adoption until you see some threshold. So you say, okay, once 95% of people are signaling that we have this new operation, we'll all enforce it. Because quite likely, the soft fork people don't want this. A lot of times you say, look, I want this new rule. I want this new signature system, or I want this new, even odd thing. It'd be really better if everyone only used odd numbers. However, I'm not willing to split off because of this, right? I want everyone on board, or at least the majority on board, so we don't have a new split and we get the new rule. This is what I want. I like the rule, but I'm not willing to, put a stake in the ground and say, look, I'm making my own network if you don't adopt it. So in order to do that, we say we want to get a majority of mining power to adopt it before we start doing it. And so that way we can signal in the header that like, hey, I'm aware of this new rule and I will enforce it if everyone else says they're going to enforce it. So sort of a staging process. So that was called BIP9. And the idea is, once 95% are signaling it, then you activate it. This didn't actually work in practice. I think it worked once with the opt check sequence verify. And then last year, people were just arguing and the miners were like, no, we're not going to activate any new soft forks. Or then they started making all these deals. It was a mess. Governance, yeah. Okay, so the future of soft forks is definitely unclear. This is very much in flux. How is this going to work in the future? How are people going to agree on these things, right? It seems, a lot of the times from the developer perspective, it seems like, why not? Like, hey, we made this cool new signature system. It's faster, it's more secure, it saves space. Let's use it. and then people say no. And you're like, well, why? Things like that. But then on the other hand, if it's like, no, we only have odd outputs, it's like, why? Who cares? Let's use even and odd numbers. Okay, so another aspect with forks, transaction replay. So this is tricky. So a split happens, let's say in the case of a minority soft fork, or a majority but not unanimous hard fork, or a full fork, something like that. There's a split, right? There's two chains that are now being extended. You make a transaction on the old chain, what happens on the new chain? I mean, guess. Yeah, sign it, and it happens on both, right? In many cases, these transactions are valid on either, and so they can be rebroadcast or relayed between the two networks. And if it can be relayed between the two networks, it will. Someone's gonna set up a little script that grabs all the transactions on one chain, broadcasts them on the other, even if you don't want them to. Like, someone will do that, right? And if it's valid on both, it gets confirmed on both. And so you say, okay, it now splits. There's now two different histories. At the time of the split, now I've got coins on both, right? I don't usually think of it when it's a short-term split as I now have two types of coins, but I do. If these extend indefinitely and they're never going to reconverge, well, I've still got the UTXOs on both. I can make a transaction here, and maybe it gets relayed here, and now they like move on both sides. Or maybe it doesn't. So you can potentially, and eventually the UTXO sets will diverge, right? How do you diverge these things? Well, if you mix it with coins that have been mined, right? So you know that the new Coinbase, the new coins here are definitely different, right? Those are going to have different TX IDs. Coins that got mined here will not exist on this one, and vice versa. So eventually, more and more coins start getting mixed in with each other, and they will diverge. That takes a while, though. Another thing you can try to doing is just spamming double spends. I'm going to send to this address. I make a transaction, Alice pays Bob. I also make a transaction, Alice pays Carol. I just spam one, send one to one place, one to the other. Hope they get in. Eventually, they'll start diverging, right? Just by chance. You can also try exploiting lock time deltas. So in many cases, the heights will be different. And you can say, okay, I'm here. I'm going to make a transaction that's only valid after block 5. And if someone replays it here, they're going to have to wait 2 blocks before it's valid. And then this gets confirmed here, and then I make a different transaction spending the coins here without a time lock. And so I can try to sort of exploit the fact that there's timing differences between the two chains to make transaction A occur on the top one and transaction B occur on the bottom one, and split my coins off that way. So those are potential ways to split your coins despite these transaction replays. And then you can now say, okay, I have 2 separate wallets, 2 separate keys on the different chains. However, yes, this is expensive. This is ugly. It's possible, but it's ugly, right? Because you're basically going to spam the network. And in many cases, you're not actually trying to send money. You're just sort of moving your own money around internally. So if everyone does that in the system, it can overload the system, have tons of transactions. Also, if you're doing this, it might not work. And you're like, okay, I just confirmed a transaction for no point whatsoever. Got to keep trying. It's pretty ugly. Also, people don't know, right? So why is this a problem? Well, in many cases, you want to sell one and not the other. In addition to these software rules, such as bonus coins per each transaction or only odd numbers allowed, there are often sort of philosophical and cultural rules that get associated with it. And people hate each other and yell at each other and insult each other on the internet all the time. I don't think this is unique to Bitcoin or cryptocurrencies. I think it's just sort of, you got money involved, you got trolls on the internet. It's a rich mixture of the best parts of humanity. So a lot of times people want to sell one or the other, right? So they say, I think the odd coin is stupid, I'm going to sell it. And I want to, someone wants to buy it, and I'll get these new coins. That's difficult if transaction replays are occurring. Another problem is that many users could be unaware of the forks. I know a lot of people, there have been a bunch of sort of full forks in Bitcoin recently, where different rule sets have been adopted. In many cases, entirely different proofs of work, things like that. I'm not aware of all of them. I know of some of them. Most people I know don't know of all of them or even any of them. So users might unknowingly send both or not be aware of these things. That's an issue. There's also all sorts of crazy legal issues talking to exchanges where like, okay, this fork happens. Do we owe our customers both? Do we only owe them the one that, and which, does the exchange have to let people decide to adopt or ignore a new rule set? There's all sorts of weird legal issues that are still being, settled. And for one example, here's what you can do: a replay attack on an exchange. And this is not a theoretical example. This has happened. So let's say the network splits, right? You get bonus coin and regular old coin. And the bonus coin has a majority hash rate, and there's no kind of replay protection, right? All the transactions that are valid in one are valid on the other. Okay, so the network splits into coin A and coin B. And the exchange is only running coin B. They say, look, this has the most hash power, and that's what defines the system. We don't, they adopted a new rule, fine. There's this new rule that you can generate a coin out of nothing. So the user says to the exchange, okay, I'm going to deposit coin B. The exchange says, yes, I acknowledge your deposit of coin B. That's the network I'm running on. I see your transaction. It's in a block. Cool. You've now got a balance. And the user says, yeah, changed my mind. I'm withdrawing coin B. And the exchange, so what happens next? The exchange says, sure, here's coin B. Oh, and coin A, right? The exchange doesn't implement any replay protection. They don't acknowledge the existence of this other chain. They don't know they have coin A. I mean, they should, because they split, they actively split, but whatever. And then the user's like, cool, I got both, right? I relayed this transaction between the two networks. I was now able to deposit only coin B and withdraw both coin A and coin B. And now I redeposit, I split again, I redeposit coin B, and I keep doing that. And so I can drain the exchange of all of their coin A with the same amount of coin B, just looping through, depositing and withdrawing. So yeah, this happens. Does anyone, I'm not going to say which exchange was susceptible to this attack. Does anyone know? It shares a name with the first transaction in a block. Anyway, so yeah, it was almost 2 years ago, like a year and a half ago, with the Ethereum Classic kind of hard fork, that happened. So that was, it happened. I'm not saying, it's not obvious, right? These are some attacks that are like, in retrospect, it wasn't that hard to find out. Like, I'm sure the people at the exchange were like, shoot. Yeah, we probably should have seen that coming. And we lost a couple $1,000,000. Shoot. It's also weird because like all of their users like generally are identified and they have like, their passport or where they live. And so you could probably tell like, hey, come on, dude, give it back. Like you're just, but maybe they didn't because they're like, well, because they might have programmed it in a way where they could sort of deny it and say like, look, I just deposited and withdrew a couple times. That's what I always do. I don't know. But yeah, there were definitely warnings. There were a lot of people saying like, hey, this is dangerous. You need to really implement replay protection. If there is a fork without replay protection implemented, the exchanges really need to honor and try to split both before offering both for deposit and withdrawal, things like that. And so there's been a lot of, last year as well, there's a lot of argument because in Bitcoin, one group of people wanted to, Segway 2X was what it was called. And they wanted to implement a hard fork and not implement replay protection. And so that was a big argument where people were saying, look, if you're going to make a hard fork, make it a full fork, make it implement so that you're going to go off, but also implement replay protection. Make it so that transactions that you guys sign are slightly different than the old way. And it's not too hard to do. What you can do is sort of, when you're making a signature, flip some bits. Well, okay, you can't flip bits in the signature itself, right? Because those can be flipped back. But what you can do is you can like flip a bit or two in the hash that you're signing, and then the old software won't be aware of that flip and say, look, this doesn't look like a valid signature, because it's trying to compare it against a different message. Or you can like append something at the end of the message you're signing, things like that. So that On the new network, the signatures look different. And that helps in terms of safety, because then like the old software that's ignoring will not inadvertently send transactions. And also for the new network, they will not inadvertently send transactions on the old network. So that's, and there's a lot of like the ideas of like opt-in versus opt-out replay protection, where you can like allow the option to sign differently but not require it. All sorts of weird ways you can do it. But yeah, this is a fairly recent, mostly like last summer or last fall, people were like trying to do different things. And so in practice, I think this is the end of the, let me go like 2 more minutes. But yeah, consensus changes are hard. In practice, there's been some full forks recently. The last soft fork was segregated witness. Segway happened sometime in September or last year. It was a mess. And there was also some full forks. Bitcoin Cash, and then later Bitcoin Gold, which is a lot smaller, and they completely changed the proof of work. And now there's sort of a bunch that are like pushing the definition of a full fork, where they're basically like also called airdrops, where it's sort of a completely different coin that just happens to have the UTXO set of the old coin. And so it's like, why even bother with the history? We're just like, look, it's a new coin that you inherit all these other coins. Anyway, so there's a bunch of those. It's a mess. It's kind of fun being, I could not have given this lecture a year ago. A lot of these things had not happened. A lot of these terms were not well defined. A few years ago, the idea of soft, hard forks were not even defined. Like, it's pretty clear that Satoshi later, after releasing Bitcoin, started to understand this system. But in the beginning, there was not like a clear understanding. Probably the biggest, contentious soft fork in 2009 was that Satoshi added a 1 megabyte block size limit. And to reverse a soft fork is a hard fork. And so the sort of block size hard fork. And then there was a very clever way with Segway to make it a soft fork, but also sort of increase the block size in a weird way that the old software wouldn't recognize. I might have to explain a little bit of Segway maybe next week. Okay, so yeah. It's sort of a feature and a bug, right? Consensus changes in these systems can be very difficult. On the one hand, you want your coins to stay put. You don't want your money to change. You want to be able to just have a bunch of money, and a year later you still have a bunch of money, and that's what you want it to do. On the other hand, new features are cool, and these are not ossified. You don't want these to be ossified legacy systems. You want this to be like new cool technology, and you go make all these new cool things. And make it faster and better, stronger. And the role of miners is also a big point of contention, right? They seem to have outsized influence in some ways, right? Up here is the mining power and how that affects things. And why should these miners have outsized influence? Shouldn't the users themselves be able to vote? But they can't, right? If the users could vote, maybe you wouldn't need mining at all to verify blockchain. So there will continue to be a lot of debate on this stuff going into the future. I hope this helped explain the general thinking as of early 2018, but it'll probably change. Cool. Any other questions about this whole thing? If you have I don't know, James helps develop Vertcoin, right? Are hard forks and soft forks difficult in Vertcoin? No. You're like, hey, we're doing a hard fork. And yeah. So in smaller communities, smaller coins where there's not as many people involved and people sort of are all on the same page, these changes can be made fairly regularly, not a huge deal. Bitcoin is very messy. Bitcoin, everyone hates each other. They're always trolling each other on the internet and hacking each other, death threats, all sorts of stuff. So yeah, future forking methods. There's probably new cool ways you could add to the bottom of that chart, some new idea that maybe works better. So stay tuned.